Ever wonder what the ground feels like during a massive earthquake? This discussion dives into the pulse-like motions of a recent earthquake in Turkey.
It's intense. We're talking about ground shaking that's not just a rumble, but a series of powerful jolts.
Like a giant shaking its fist.
Exactly. And these jolts, these pulses, are what caused so much damage. Yeah.
So how do scientists even study something like this? Let's start with the basics. What made this earthquake so significant?
It was a massive 7.8 magnitude quake striking near Kahramanmaraş, Turkey. The devastation was immense. Thousands of lives lost and widespread destruction. It was awful.
And it wasn't just one quake, right?
No, there was a powerful aftershock shortly after and several more significant tremors. The whole region was rocked. It was terrible.
So how did researchers get a handle on what was happening underground?
They used strong motion data from over 100 seismic stations within 200 kilometers of the fault. That's a lot of data.
Wow. And what did they do with all that data?
They used wavelet analysis, a technique that helps to isolate specific signals within the complex earthquake recordings. Think of it like separating different instruments in a busy orchestra.
So they found these pulses. What exactly are they?
These are short bursts of intense ground velocity. Imagine the ground suddenly looching forward and then back with incredible force. It's crazy.
Right. And these pulses are what caused the most damage?
Absolutely. They're far more destructive than the typical shaking we associate with earthquakes.
Where did these pulses occur? Were they everywhere?
Mostly near the fault line, within about 20 kilometers. Further away, the pulses were less common and had different characteristics.
Oh, interesting. Different how?
Closer to the fault, the pulses were unidirectional, like a single powerful shove. Further out, they were bidirectional, more like a back-and-forth motion.
How strong were these pulses?
The strongest reached an incredible 220 centimeters peak ground velocity. That's a huge amount of movement in a very short time. Amazing.
Wow. And how long did these pulses last?
The duration varied from a couple of seconds to over 14 seconds. The longer ones were particularly damaging.
How did these pulses affect buildings and structures?
They amplified the response spectra, particularly at longer periods. This means that structures designed to withstand typical earthquake shaking could be severely overstressed by these pulses.
So existing building codes might not be sufficient?
Exactly. The study shows that standard models significantly underestimate the impact of these pulses on long-period structures.
So what's the big takeaway from all this research?
We need to better understand and account for these pulse-like ground motions in earthquake engineering. Building codes need to be updated to reflect the increased risk.
It sounds like a call for more robust building designs, especially in areas prone to these types of earthquakes. What kind of research needs to be done next?
More research is needed to refine our understanding of pulse generation and propagation, and to develop more accurate predictive models. This will help engineers design safer structures.
So what does this mean for people living in earthquake-prone areas?
It highlights the importance of building codes and regulations and the need for stricter enforcement. Public awareness is also crucial.
The study mentions rupture directivity. What's that?
That's the direction the fault rupture propagates. The direction of the rupture significantly influences the intensity and characteristics of the ground motion.
How does this earthquake compare to others around the world?
The intensity and duration of the pulses were comparable to other major earthquakes, but the sheer scale of the damage highlights the devastating potential of these pulse-like motions.
So this research really underscores the importance of understanding the nuances of earthquake ground motion.
Absolutely. It's not just about the magnitude, it's about the specific characteristics of the shaking and how those characteristics affect structures.
That was a great discussion. Thanks for sharing your expertise.